and give you guys a good lecture. This is probably, I think this might be my final lecture for you guys. So thank you guys.
What you mean? Where you going?
Friday I'll be in the clinics. Friday I'll be with Mr. Donnie visiting the clinics. I might be in the class at the end, but we'll
So
see.
you're gonna see all the techs that don't want to be there, that don't want to be there.
So,
He sees that either way. You sure too.
so we left off last time. What's up? What's up? I got the glasses.
The
too.
whole ensemble.
Whole thing.
Look.
Down to
And the
cool-
pens.
He's looking. No. Oh,
Yeah.
exactly. He didn't catch it. We should have. You should have seen what he was gonna say.
Let me see the whole thing.
They saw you.
They're Pumas too?
No, let me see it from the front.
Oh man.
Those shoes are really cool.
Yo, down to the brand. Literally.
Really?
Both of them are Pumas.
Yeah.
Both of them are Pumas.
Yeah.
Identity theft is not a joke, Jim.
Yeah, it's not entirely there, but
Oh man, it was just so funny because Mr. Phung looked at him up and down.
I don't know. Wait a minute.
That's a coincidence, right?
I don't know how I feel about this.
How did you did that?
we gotta take a
Is
picture
that your
after this.
Halloween costume? You guys should take a picture. You heard me?
We will.
Copy and
Is that your
paste.
Halloween costume?
This is my Halloween costume.
Oh.
Alright guys, now let's seriously let's get back on track here. So we left off on half value layer last time. Does anybody want to try and explain what half value layer was? Anybody?
Take the half, the half, the half, the half.
Half and a half and a half and a half. Yes, so half value layer. So we have our beam, our X-ray beam coming in at 100% of 100% without any filtration. We add one half value layer that cuts that beam by 50%. So now only 50% of those X-rays are passing through. If we add a second half value layer, that half gets cut by half, and so on and so forth. So remember, we have our 50, 25, 12.5, 6.2. As we add half value layers, we just keep cutting the intensity by half.
And just to double check, when we say intensity, are we referring to quality or quantity?
Quantity.
Is it, who thinks it's quality?
No, quantity.
For the intensity?
For intensity. Who thinks intensity is quality? Right? Who thinks intensity is quantity?
I think it could be both, right?
All right. And Anthony, what is the answer?
It would be quantity.
Intensity is quantity. So when we talk about half value layer, we are talking about reducing the number of X-rays. The quantity of X-rays. That is how we reduce our intensity. Okay.
That's pertaining to the filtering, right?
What we're filtering.
Correct.
Cody?
So if you flipped it, would you say penetration instead?
Penetration will be carried.
Very good. Penetration is quality.
Thank you, Cody.
Energy of the beam is quality. The power of the individual photon is your quality.
So,
Sure.
I have a question. Oh, I'm sorry. This is
What's
out
fine.
of habit. Anthony, is it directly proportional to the quality? The quantity, is it directly proportional to the quality? If the quantity is reduced, the quality will be reduced first.
No, so they are two different things. Quality and quantity are two different things.
So-
Again, quality is referring to the energy of the beam and the penetration of the beam. Quantity is just the number of X-ray
But if
photons.
the number of X-rays are less, then the energy is less of
Not necessarily. No, you can have the same number of X-rays with a different level of penetration power. Right?
So let's think of it this way, right? Let's say I have a bag of ping pong balls, right? And I start throwing ping pong balls at you guys, right? If I throw one ping pong ball at a time, right? Versus grabbing a handful and throwing them at a time. What is the difference there? There's a difference in quantity, right? One ping pong ball, lots of ping pong balls. Did the energy change? No, ping pong ball
It's
hurts,
not ping pong ball.
hurts the same, right? Each ping pong ball hurts exactly the same. But now, instead of a bag of ping pong balls, I grab a baseball and I throw it at you. Does that hurt more?
Yeah, the energy will change.
More energy in the baseball, right? So that's the difference between quantity and quality. They can change individually. I can throw one ping pong ball, I can throw a lot of ping pong balls. I can throw one baseball, I can throw a lot of baseballs. Right? The quantity does not change the quality. The quality does not change the quantity. They are separate concepts. So if I want to penetrate something, right? If I want more penetration, am I going to throw more ping pong balls?
No, you need more energy.
No. I'm going to switch to a baseball, right? But if I want more things hitting the IR, what am I going to do?
Quantity you increase.
Right, I'm going to increase my quantity. I'm just going to throw more things.
All right. So, it, no.
So just making sure intensity is quantity.
So, Mr. Phung did let me make some of these slides myself, so I don't know if you guys noticed the difference.
That's about the same.
Looks about the same. So, we're gonna go over primary and remnant beam and what
Is that a
means.
compliment? If it's the same as the points. That's a compliment.
Well, they both look good. So, we know once we hit our button, we know something goes on in the tube. We know the electrons get shot over to the anode side. There's target interactions there, which we went over before, which are our Brem's interactions and our characteristic interactions. Now when that happens, X-rays are produced. Those X-rays exit through the port, and then what happens? You see they go, hit the patient, and then hit the IR. When those X-rays exit the port, before they hit the patient, that's referred to as the primary beam. After they hit the patient and exit the patient, that will be our remnant beam. Okay? So, X-rays exit the tube, enter the patient, and exit. When they exit, they'll either be transmitted straight to the IR or they can scatter. Whether they scatter or whether they're transmitted through the patient, that is still part of the remnant beam. Yes, Jay.
So the remnant beam is a different beam than the primary beam, but would you say that like the X-ray that is shot is not the same like that's getting to the IR? That's the remnant beam at that point.
So it starts as the primary beam, and then as it goes to the patient, that exit radiation is the remnant beam.
So that's what we're actually visualizing.
So some get absorbed, and
Some.
then the ones that are transmitted
Mhm.
out will be the remnant.
Correct.
So
What
you
I
two are
read-
both very close.
So
Sir, what I read was
what
what
are we
hits the
seeing?
IR is the remnant
The-
beam, but what does not hit the
So
IR
some
is the
get
scattered.
scattered.
from-
All right, so yes, so let's clear this up. Primary beam is the X-ray beam that is going to reach the patient. Right, so between the tube and the patient, those X-rays form what?
Primary beam.
Primary beam. Secondary beam are going to be the X-rays that come from the patient and hit the IR. So between the patient and the IR, what do you have? Remnant, right? That's your secondary or your remnant beam. Now, what makes up your remnant? Well, in between your primary and your secondary, there's a patient. The patient is kind of in the way of your beam. And in the patient, three things can happen that we talked about before, right? What are one of those things, Samantha?
What are the things that?
What can happen inside the patient? Give me one thing that can happen in the patient. When an X-ray reaches the patient, what is one thing that can happen to the X-ray?
Like, I mean, you're talking about like leakage radiation or scatter. Okay.
Okay, scatter, yes. So one thing that can happen is X-ray reaches the patient, it scatters. Good. Carlo, what is something else that can happen? It doesn't go through at all. Good. What is that called? classmates are trying to help you.
Jealous.
Absorption, very good. So we have scatter, we have absorption, and Angelica, what is the third one?
You have what?
We have scatter, we have absorption. What is the third thing that's in here? Transmission, very good. Absorption, scatter, transmission. Of these three, absorption means the X-ray stops. It cannot continue. So will you have any photons in the secondary beam from absorption? No, because there are no photons from absorption. Will you have photons from transmission? Yes. So that photon from transmission is the same photon from that primary beam. It just went straight through the patient, no interactions. It has not changed at all. It just made it all the way through, dodged all the obstacles. What's the third one? Scatter. X-ray hits the patient, it bounces. If the X-ray hits the patient and it bounces back towards the tube, is that secondary radiation? Is that your remnant beam?
Yes.
No, because it's not going to the IR. If it bounces off the patient and goes back up to the tube, it's not going to the IR. So it's scattering away from the IR. What if it bounces, but it's still going in the direction of the IR? Is that remnant radiation? Yes. So it can reach the patient, it can change direction, but it still gets to the IR. So what are the two things that make up remnant radiation?
Scatter.
Transmission and scatter.
So the scatter has to reach the IR as well.
Remnant radiation is the radiation that reaches the IR.
The remnant is indirectly reaches it and
There's no
remnant
indirectly
is direct
reaching.
and scatter is indirect.
There's no direct or indirect.
So what's the difference between scatter and the remnant? Sir?
Scatter is a type of remnant. Remnant is your category. Under your category, you have transmission and scatter. But both of these have to do what? Reach the IR. If it does not reach the IR, is it remnant? No.
Thank you, Mr. Phung. All right.
Emily had a question.
Emily has a question?
So just clarifying, if it's absorbed, then it's still part of primary because it doesn't reach the IR?
It's nothing.
It's nothing.
I have your
It's
opinion.
not. It's neither part of the primary nor remnant. It's just
Primary is
It's gone.
before it hits the patient.
primary is before
Okay.
consultation.
So we're already visualizing the remnant.
Yeah, remnant is radiation that exits the patient and reaches the IR.
In absorption is primary.
Absorption is nothing. There is no more photon after absorption. The photon's gone.
Yeah, so it won't be a part of either of these.
And the only way to track that is through the math and stuff that we've gone over, like Rankins and Sieverts, all those SI units, to like actually account for the absorption.
So we'll talk more about this next chapter, but as far as absorption goes, absorption is going to be your primary contributor to patient dose. So yes, when we talk about dose for the patient, we're mainly talking about absorption.
So moving on, we're going over the emission spectrum now. The emission spectrum is this graph here. It's a visualization of the energies created, the range of X-ray energies that are created through our Bremsstrahlung and through our characteristic interactions. As you can see here, this purple line is like what our characteristic, and these are known as our discrete values. Bremsstrahlung, this pink line, is our continuous values. Now, the x-axis here is the X-ray energy that is produced. Our y-axis is the number of X-rays that are produced. So, how many X-rays we have versus how strong the energy is. So, what would our x-axis be in terms of property of the beam? Is that our quantity or our quality?
Quantity, number of X-rays.
It would be our quality.
Quality or quantity?
Quality. That's our energy, so that's our quality.
Yeah, but that's the number of X-rays you said.
The number of X-rays is going to be our y-axis, which is our
Quantity.
quantity. So, does anybody know why there's a difference between how these lines look?
Characteristics has a set value, and Bremsstrahlung kind of just, it depends on how slow or how much it slows down. Like when
Correct.
it gets closer.
Correct.
The other
So-
one is always set numbers.
Correct. So because it's a set number, it basically stays right here on whatever that value is. Bremsstrahlung, it can be either, it just depends on how hard it breaks when it gets near the nucleus. Because the energy that's produced through Bremsstrahlung is the difference between the energy of the incident electron versus the,
Was this the
it's
energy
the
of
incident electron, and then it breaks, and how much energy it loses from that breaking as it gets near the nucleus. That releases a photon, and that
the
photon,
orbital electron?
the difference between the how hard it breaks and the energy it had incoming. So depending on how hard it breaks, it can either be small or high energy value. Is that making sense, everybody? Okay. So we've talked about some other things about things that can affect our being quality, our being quantity. Does anybody know what kind of things would affect that? Anything that we talked about before? What's that, Tom?
I'm sorry, what is it?
So we've talked about things that have affected our quantity and our quality before. Does anybody know, like, say for example, what affects our quantity of the beam? KVP and mass, those are examples of things that will affect the properties of our beam. KVP will affect the quality, mass will affect the quantity.
Filtration.
Filtration, that's another one. Distance shielding goes along with filtration for shielding. So this is basically the graph of those energy values. Oh, where's mine? Oh, what are you doing?
What are you doing up there?
Oh, thank you, Mr. Phung. You brought my information. You're welcome. Thank you. I appreciate that.
Oh my goodness.
So this is the discrete emission spectrum. So like we said, the characteristic interactions, those are set values. So they're discrete values. Each bar represents an energy value, and the height of the bar represents how many photons are at that energy value. So these are pretty pretty solid. There's not much else to it. It's just how much energy it has, how many photons are there.
Was that before the one chip challenge?
That was for the one chip challenge. That was.
Oh, good memory.
How did you remember a
Alright,
single
so-
frame?
Let me ask you here, based on this graph and based on what you've learned, look at that rightmost blue bar. What energy level do you think that rightmost blue bar is at?
69 and a half.
Right.
Above 70.
That's the
All right, so,
What are you asking?
okay, so who thinks it, so I heard several answers, so let me see if I have that. Who thinks it's 70? All right. I also heard, who thinks it's 69.5?
We can't do that.
So, what is the x-axis label?
Energy.
But yes, what is the label of that x-axis one more
Number
time?
of X-rays.
No?
X-ray
Number
energy.
of X-rays.
X-ray energy is the x-axis, right?
X-rays.
X-ray energy is your x-axis. This discrete emission spectrum, what kind of interaction does it show you? Does it show you characteristic or Bremsstrahlung?
Characteristic.
Characteristic. What is the highest characteristic photon you can create?
69.5.
69.5. So what do you think that rightmost blue bar is?
69.5.
69.5. There we go. Okay, so it cannot be 70. Why not?
Oh, I was trying to knock it out.
Because
so I
already
said
it is not
70.
now it is 69.5.
Right.
Yeah, I know.
You cannot create a 70 keV characteristic photon.
I thought
So most places or most graphs will just round this to 69. Right, a 69 keV photon.
That's not fair because 69.5 should be rounded to 70.
No, it will not go up to 70. Your K shell is 69.5. It is impossible to create a photon higher than the binding energy of your K shell.
Bless you.
Thank you.
Bless you. So no.
Oh, you could round it. Eight actually.
And if we were going to be specific, Shaheen, the highest energy photon is not actually 69.5. It's actually 69.498.
Or they're already rounding it.
Sorry, 4992.
So they're already rounding it, so then they can't round further.
So, no.
He said, y'all
That
started,
brain.
he said, y'all started, so I finished it.
All right, I'm sorry about that, Anthony.
Oh, good.
That brain.
All right. That's right, I left.
Oh, he left. He might be back.
How are you doing that, so?
All right. Continuous
Are
emission
you
spectrum.
not doing it, Anthony? How
Yes.
You're making us.
PowerPoints. So continuous emission spectrum. So these are going to be our Bremsstrahlung interactions. The ranges go from 0 to the maximum KDP value that we set. The height represents the number of photons at that energy. And then the x-axis once again represents the energy value for these. Now most photons have about 1/3 of the maximum KDP, so that's going to be around the peak right here. And that's going to be about 1/3 of the maximum KDP. That's where we'll find most of our photons at energy points. So let's see. If this is a maximum KDP of about 100, what do you think the peak would be?
Peak is
maybe like 35.
80, yeah.
35, okay.
Oh, I see.
30,
Because if
35.
not for the maximum,
So about 1/3 of 100 would be about 33.3. Good.
That's good enough.
is that because 33.3 is a given amount? Or?
It's because the maximum KDP is 100, and most of our photons in Bremsstrahlung interactions are going to be at about they're going to have about 1/3 energy of the maximum KDP. So if the maximum is 100,
So if you change the maximum, like say to 50,
then it
then
would
it'd
be
be a third of 50.
a third of 50. Exactly.
Right. Which is? That's right, 16.7. Very good. Let's continue on.
So we mentioned some things that affect our quantity and our quantity of the beam. So this is how we visualize that. For example, this is the effect of MA. If the MA increases, it's going to increase the number of X-rays. It does not affect the average energy of the X-rays. MA will not, so it would not have any effect on the quality of the beam, only the quantity, which is why the peak energy that we have is not moving. It stays in the same area, only the number of X-rays will increase. Yes, go.
And is this one we're talking about, I think it was like the continuous?
Correct.
Okay. So this is happening for more of the Bremsstrahlung than it is the like the characteristic, because the characteristic doesn't look like it's done anything, even with like the increase of like the number, I guess. I mean,
Yes. So that characteristic really
doesn't really change.
doesn't change at all. It just kind of caps out.
Right, because then it's set. Okay.
It's a set amount.
Yeah.
Yes.
You said the MA doesn't have an effect on quality?
On quality, yes. On energy.
Okay, thank you.
What is an effect of the amount? Sorry.
The MA.
The MA.
The mass.
No. MA is not mass.
Is it?
So-
So the second.
Where's seconds?
It's not second,
Exactly.
but it's the same thing you're talking about.
Before we move on,
It's not the same.
does anybody have an idea, if we're talking about MA, does anybody have an idea of how KVP might affect this, this emission spectrum?
The peak is gonna go, right?
It's gonna go right. Veronica, did you know?
Peak can go down.
Yeah.
That's it. We're talking about what happens if KVP changes. So let's say, for example, we increase our KVP.
It's gonna be higher.
It's gonna be higher.
Energy is gonna be higher,
The energy is gonna be higher.
but the number of inches won't go up.
Okay.
I think the energy is just gonna change over to the right, but the actual height of the, let's say, the way it doesn't.
So both of you think the same thing?
I think.
All right. So, does anyone else have a different prediction? Right? Well, we already changed it. So, all right. Sorry. So, how do our predictions match up?
So, we see that indeed the peak did move over to the right, so that did increase. But the height also increased, so the number of photons also increased. Remember, KVP does increase the penetration power of the beam, so the energy, but it also does have an effect on the quantity of the beam.
They're directly proportional. KVP increases the amount of X-ray increases. X-ray increases, KVP increases.
Yes, but they are not directly proportional.
Correct.
Little bit is increase, it doesn't repeat.
So, you still have that other old slide on
Which one?
the old KVP slide.
Old KVP?
Yeah, if you go all the way back. Go back like 6 slides.
Ah. There we go.
Sorry, go back.
Go back.
First one?
This one.
Ah, there it is.
Do you remember the slide from last week, or from Monday?
So, mass, if it increases 2 times, the quantity 2 times, so it's directly proportional. KVP, if we increase KVP 2 times, we'll increase the quantity by 4.
A square of the.
So not directly proportional, but it does increase it by a factor of, what would it be, 2?
So KVP changes by a factor of 2, quantity changes.
By a factor of 4. Alright, so is it making sense why that's happening? Yes, no?
Yeah.
By what is happening?
This change in the emission spectrum.
So basically, if you wanna change the mass, it's only
How is your
gonna change the
calculated
number of
spectrum?
photons.
It is gonna
But if we're
change
gonna
it.
change the KVP, the energy is gonna change the energy and the amount of
There you go.
photons.
Correct, so it affects both. KVP will affect both the quantity and the quality.
Now I do want to point out one more thing. The peak of the spectrum has moved which direction?
To the left.
The peak is, so going from green to pink, the peak has moved towards the right, and it's also moved which way? Up, good. But look at the blue line. Did the blue line change left to right?
No.
Why not?
Because that's the standard, that's the characteristics of.
It's the straight.
Good, characteristic, standard, always the same, right? So, the peak is which interaction? The brems. And so the brems is changing, but the characteristic is not.
And this all has to do with the emission spectrum thingy? Is this what we're
Emission
talking about?
spectrum.
Okay, so if you increase the KVP, it'd be 4 times.
Also, when you're saying about characteristic, you're saying there's a characteristic production of X-rays.
What about it?
Is this, when the characteristic here is referring to the characteristic production of X-ray?
Yes,
The two productions of X-ray here, Brem's and the characteristic.
yes.
Oh,
Also known as discrete and continuous.
So now the effect of filtration when we filter out X-rays. We talked about some type of filtration earlier. And here's how it will affect the emission spectrum, how it will affect the beam properties. So if the filtration increases, the number of X-rays is going to decrease because we're filtering out those low energy photons. So the total number is going to decrease. And because we're taking out those low energy photons, that means our average energy is actually going to increase because we're hardening the beam. So as you see, we go from the pink to the green, we add 4 millimeters of aluminum filtration, so that's going to drop the total number of X-rays, but our peak is moving to the right. So we're increasing the average energy of that beam. Once again, a characteristic stays the same. But what's going on down here?
Cut it off.
It's cut off. Why is that cut off?
The hardening of the beam.
Because we're filtering out those low energy photons. So they're not going to appear anymore.
All right.
Oh, but it's this way.
So let me ask you all a question here. Take a look at the height of that pink peak. If I wanted to drop the height of that pink peak down by half, how much filtration would I need? If I wanted to make that pink peak half its height, how much filtration would I need? And I'll give you a hint, I am not looking for a number.
Sounds about right.
Increase something.
How much?
Okay.
Oh,
We do not have filtration.
you
You
increase
do
it
need
by 2
filtration.
millimeters.
No, not 2 millimeters.
4 millimeters.
If I want to drop the height, I'm reducing the number of photons,
Oh.
right?
But the half,
I need filtration.
the half level, whatever. I
A
can't,
bit louder, Cody?
the half levels, I can't remember.
Half level, it's very close.
Yeah.
We're getting there.
Half value
value layer.
level, almost.
Layer.
There we go.
Good. We need to add 1/2 value layer worth of filtration
That's 2
to
millimeters.
drop the quantity down to 1/2, right? That is the definition of half value layer. You add a half value layers worth of filtration, and the number, the height of the peak, will drop by to 50%. Does that make sense?
But this is not 50%, is it, sir?
That's not 50% on the graph, no.
No.
So that's why it's not 2 millimeters.
Oh, I see.
I don't need a number. All you need to know is that it's 1/2 value layer. That's the concept I need you to understand.
That's the minimum you can drop, is the 1/2.
1/2 value layer will drop you by 50%. 2 half value layers will drop you down to what value?
25%.
25%. Very good.
6 half value layers would be.
No, negative you can.
Alright, so we understand how
That's
filtration.
the number of it.
Number of X-rays. Correct.
So we understand how filtration affects. We're lowering the number of X-rays and increasing the average energy. Another factor is our generator type. I know we've talked about generator types before. We have our single phase. Anybody remember any others?
Single, high,
3-phase,
3, 6.
6-phase,
3-phase 6 pulse.
12-phase.
I heard someone say high frequency. So the type of generator that we have affects the properties of the beam, the quality and the quantity. So if the generator type improves, the number of X-rays is going to increase, and so will the average energy of the X-rays. So as we get a better generator, we're going to be able to produce higher energy and more X-rays.
And as a preview for your next semester, Anthony, what is that R word that is responsible for this effect?
The R word?
Yes.
Oh, the rectification?
Looking for a different R word.
A different R word?
Percentage.
I feel like
The percentage of change.
the percentage of change.
Yes.
Oh, the ripple.
The ripple. Very good. So next semester you'll learn about generators, you'll learn about generator ripple, and that will explain why the quantity and quality of your beam changes with the generator. But for now, just memorize this, please.
Yes, ma'am.
And you know how we're taking all these classes, is the test divided for like, let's say 20% for this, 20% that, or it's just weird, you just don't know when you're gonna get it.
It's on the website. The ARRT. It shows the number of questions from patient care, number of questions from proceeding.
So, once again, as our generator type improves, if we go from a single phase to a 3-phase, we see that the number of X-rays we're able to produce increases, and then the same thing happens when we go to a high frequency. And every time we improve that generator, the average energy moves over to the right as well. So we're increasing the average energy as well.
So the filtration decreases both in the generator.
The generator will decrease the number of photons, but it will increase the average energy. Remember, because we're filtering out the lower energy photons,
The generator?
the filtration.
Oh,
That's what you're saying, right?
yeah, filtration.
Please.
Never mind.
What do you mean?
Yeah.
What do you mean by the horizontal
The person
rotation
who's
of
right.
The number of
peak
filters.
The person who should argue, the walk.
in the graphs?
So this peak, remember, the peak of this line here, that's the highest, that's about 1/3 of the maximum kVp. So that's our peak, because most of our Bremsstrahlung photons are going to be at about that energy range. Most of them are about 1/3 of the maximum kVp. So we describe that as our peak. So as the energy of the X-rays change, that peak will move either left or right, depending on the average energy increases or decreases.
The peak is the horizontal level of the peak, is the same thing as the peak. So
That peak is that right there, the highest portion of this line. Alright. Everybody good on generator types? Good. Target material also affects this emission spectrum. If the target material change, it'll affect the number of X-rays. It'll also affect the average energy. And generally speaking, the higher the atomic number, the higher number of X-rays, and the higher average energy of the X-rays as well. So what target material does our anode target use? Tungsten. And that's why. Tungsten has a high atomic number, so we're able to produce a large number of X-rays and have a high amount of energy for those X-rays. Yeah, I'm blinking a lot today.
That's how it is sometimes.
It is. Jay, yes.
Is gold Z and molybdenum Z like a specific alloy of those elements?
That one's
Or-
a bit out of my scope.
So what does the letter Z mean? Do you remember from physics?
zinc, no, zinc is that.
Oh, yeah. Z is the atomic number,
Oh, I didn't know that.
correct?
Correct. Z is the atomic number. So if you look at the second to last bullet, generally speaking, the higher the atomic number, the higher the energy for the X-rays, the more X-rays they're able to produce. So because gold and tungsten have a high atomic number, right, 79 and 74, they are going to be able to produce high energy X-rays, and a lot of them, right? Elements with a low atomic number, so for example, rhodium, atomic number 45, molybdenum, atomic number 42, they are not able to produce as high energy X-rays because the binding energy of that K shell is going to be much lower. So the Z is just telling you what the atomic number is, so you can kind of see the pattern between high versus low atomic numbers.
Why did they choose not to give, why did you choose not to give the rhodium?
You can ask the author. You might be able to meet him at TSRT.
Oh, I thought he's the author of the,
I don't know the author of the book.
oh,
I didn't read the book.
I did the PowerPoint, so you must.
I definitely read the book.
All right, now let me ask you some. Or sorry, Cody, go ahead.
Is gold common? Because like, I don't know if I feel like the melting point for gold is probably like lower than tungsten.
All right, very good. So, as you can see, gold is actually even better than tungsten at producing X-rays, right? But why do we not use a gold target instead of a tungsten target?
It's expensive, so.
No, it's not because it's expensive. Tungsten's expensive. No, gold's gonna melt. You fire electrons at your gold target and you're gonna have a melted target in no time. Right? You're just gonna have a blob of gold inside your tube. So why do we use tungsten instead of gold?
Because tungsten has a higher,
Heat resistance.
Right.
higher.
X-ray production is not our only concern. We also need to worry about the heat resistance of the metal. Okay, so great observation.
Take a break.
Do you feel like it?
Let's take a break real quick. It's getting hot in here.
All right, so right now it's 2:13. Let's take a 10-minute break. Please be back at 2:25.
Thank you.
2:25.